Y3, electric field. This plot shows the electric field lines due to 2-point charges QA and QB on the plane. The two charged particles are placed at these coordinates on the XY plane. We find that electric field around B is converging to that point. Electric field near the point charge A is diverging from that point. Electric field from positive charge diverges, so it is a QA is a positive, and negative charge converges to that point, so this QB must be negative. We find that at point X, on the left side, the electric field is to the right, and on the right side of X, it is coming to the left. Therefore, they meet together at point X, and there is no arrow at this point. This means electric field vanishes at this point. Electric field far away from the origin. Here the central point is the origin, A minus A. And very far away from these two charges, we find all of the electric fields are coming into. There's no arrow going out of this. Therefore, if we consider the sum of the two charges, we think the sum should be negative. Therefore, very, very far away, we can make an approximation. The sum of these two charges, a single negative charge, very far away. So electric fields are toward the center point. Next, we have 1, 2, 3, 4 charges, and electric field due to these 4 charges are drawn in here. As we have done with the first case, we find that there are 4 points where either it is converging to that point or it is diverging from that point. Oh, no, not this. X, Y, Z are the points where the electric field vanishes. First of all, very far away from the 4 charges, we notice that the electric fields are all going out of these regions. Therefore, the sum of the 4 charges are positive. In addition, everywhere near every charge, electric fields are coming out of those charges. So we think all 4 charges are positive because it is stated that A, B, C, D are one of Q0, one of Q0, 3 times Q0, 9, 27 Q0s. All right, here, distance D between A and X and B and X. Here, electric field vanishes. From this, we expect that electric field due to B is stronger than the electric field due to A. Therefore, the electric field vanishes near A rather than B. So the magnitude of the electric charge of A should be smaller than that of B. In a similar manner, we can find all these results. Collecting all of the inequalities, we find that the electric charge of A, B, C, D are ordered like that. We show the electric field lines due to three charges. These arrows are drawn in three-dimensional figure. Green particle is electrically neutral. Why? There is no modification near this point. For example, red charge emits electric field everywhere. So this one should be positively charged particle. But both this green one and blue one does not modify the electric field. We think both of them are electrically neutral. The red particle positively charged. The external electric field is negligible because the electric field lines are spherically symmetric about the red charge. Yes, there is no other charge near there because there is a symmetry between left and right, up and down. There is a spherical symmetry of the electric field around the red charge. So we expect that there is no significant charge distribution around near the three charges. Number 4, we have an electric field. This is magnitude, and we have a plane, XY plane. We choose the positive z-axis in this way, and here z is a positive and z is a negative. When z is a positive, electric field is parallel to E3. So we expect that E is positive. If E0 is a positive, electric field is like that. Okay. And there is no other contribution along E1 and E2. The charge distribution is isolated on the plane z equals 0, right? Only at this region, the direction of the electric field changes. So we believe that if E0 is a positive, this plate is charged with positive charges. The electric field is being emitted uniformly from the plane z equals 0. Yes, xy plane is z equals 0. Has a uniform charge distribution that is a positive. Yes, if it is not uniform, there should be some component, non-vanishing components of E1 and E2, but they do not appear. There are finite discontinuity. Yes, their electric field has a discontinuity at z equals 0. And if I subtract this one, the difference is 2v is 3. This is the reason why the electric field is distributed on this plate. Number 5, electric field decays it decays. It's proportional to the square root of x squared plus y squared. So this is a planar radius direction from the z-axis. We have a z-axis, we have a rho and rho, this position vector xy in addition z, but it's a perpendicular distance is only concerned in here. And rho, E rho is a unit radial, planar radial vector. So there should be somewhere we have a x-axis and y-axis, a z-axis, and this is the angle phi, the azimuthal angle. The charge distribution is isolated on the z-axis. Yes, only if it is the case the electric field is radiated from this, and it does not have any z component of the electric field. It is a radial direction on the plane. Because the electric field does not have E free component, yes, E free component, the charge distribution must have translational symmetry along the z-axis. Yes, the charge, amount of charge with the delta z in here, amount of charge in delta z over there, the amount must be the same. Only in that case, the up and down symmetry makes the electric field vanishing along the z-axis. C. The electric field is being emitted uniformly from z-axis perpendicularly to this axis. This uniform does not mean it is a parallel to a plane. It is a uniformly divergent from a single line along the z-axis. The uniform charge distribution along the z-axis has the sign the same as that of E0. Sure, if E0 is a negative, it should converge to the z-axis. So we have assumed that E0 is a positive so that it diverges. But in case E0 is a negative, then it converges along the z-axis. The strength of the electric field decreases inversely proportional to the perpendicular distance of rho, the planar radius from the z-axis. That's right. Number 6. Positive charge Q is uniformly distributed on a semicircle. This is a semicircle of rod on the xy plane. The radius is r, and the center of the circle is at the origin. Yes, we have phi, and this coordinate is our cosine and our sine, and it is on the xy plane. The z coordinate is 0. This azimuthal angle is from 1/2 of pi until 3/2. Symmetry guarantees the electric field at O in here is parallel to E1. Right. There is a symmetry. There is no charge distribution up or down. So we do not have any z component. Second, there is no direct electric field along the y-axis because this contribution, they must have some symmetry. This contribution will generate the electric field along this direction, and the other half will contribute to the electric in such a manner so that the resultant electric field along the x-axis. If it is positive, then electric field along the x-axis. If the charge is negative, the electric field will be along this direction. Okay, a vector PO, PO, where is a PO? P, O. From this point where electric charge is placed to the point O, we are computing the electric field at point O. So O is the origin and this is a field point at which we measure the electric field. Okay, because the position vector of P is this, PO is O coordinate subtracted by P coordinate. So this is nothing but the negative of this coordinate. The unit vector n hat, unit vector, along PO. Yes, this we put n hat. So except for the radius, we have a unit vector that is parallel to this vector. The charge density, the uniform charge density of this charge is the net charge divided by the length. The circumference of the is 2 pi r, but this is semicircle. We have divided pi r. The charge, infinitesimal charge dq, can be computed. dq is the charge density per length multiplied by the arc length. We have radius r and angle d phi, and r d phi is the arc length, r d phi. To substitute this one in here, we have r cancels, the q over pi d phi. Electric field can be computed 1 over 4 pi epsilon 0. Charge, this one, we substitute this one, divided by the distance squared, and n hat is the direction from the charge to the field point, right? So we multiply the unit vector in here. So combining everything all together, we find this. And there is a trivial integral from 1/2 of pi to 3/2 of pi. Integral table can be used to find the value for the electric field at the origin. As we have expected, if charge Q is positive, it is toward the x-axis. If the charge is negative, it is backward. Next, we consider the electric dipole. We have negative charge minus Q at one edge, and the other edge opposite, we have a positive charge Q. The length of each edge is A, and we have listed the basis vector for the Cartesian coordinates. The net force on the red charge, Q, we have external electric field, that is constant electric field. Due to this electric field, plus Q multiplied by external electric field, applies to this charge, that is this, right? And in addition, the electric field due to this the blue charge can be computed by 1 over 4 pi epsilon 0 and the product of two charges, that is a minus q squared, and distance, this is a, so this distance is, this is a, this is a square root to 2a, and this is a square root to 3a. So distance squared, and there's a unit vector that connects the negative charge and positive charge. So that that can be simply computed because this, and this, right? E2 has negative sign because this direction is this direction, right? From the charge to the field point. When we compute in here, from the charge to the field point. Okay, so that unit vector is obtained like that. So if we consider this, we are able to compute the electrostatic force applied to the red charge. We can also compute the electric force on the blue charge. The contribution of the external electric field is the same except that we have negative sign on it, and contribution of the positive charge in here, we don't have to compute it again. We can apply the action reaction law. So flip the sign, then they are the same. The net force on these two charged particles, we call this an electric dipole. They are the same in magnitude but opposite direction. So net force on an electric dipole always vanishes. However, there is non-vanishing torque. That is R cross P. We can measure the torque relative to the origin placed at the center. Because the distance is, this one is a square root of 3, this distance is 1/2 of square root of 3. So, sure, you have to multiply the length of the edge A. R cross F force. There is no contribution of this force because R, the line connecting these two charged particles, is parallel to the electrostatic force due to the force shared by these two charges. That is called the central force. Any central force does not contribute to the torque at all because the cross product is vanishing exactly. So we can compute this contribution of the external electric field. Positive charge has this force and negative charge has this force, but this direction of the force and direction connecting the two charges, they are not collinear, so we have non-vanishing. They are the same, so they adds up by a factor of 2. The final value for the net torque on this electric dipole is non-vanishing. We see it is the contribution comes only from the external electric field, and there is no contribution of mutual communication due to the electrostatic force between the two charges. Number 8, this is a simple application. You can do it yourself, or let me pass this one. Detailed explanations are already given in here. Next, we consider the case. We have a circular electric charge, and there's a field point that is on the symmetry axis of this ring. We expect that if there is a positively charged, and if our net external electric field due to the circular charge is along this direction. Symmetry, because of the symmetry, only this direction survives. We can do the integration by making use of previous results. Electric field over a factor, charge, distance squared, and distance is this distance. And the direction must be from the charge to the field point. This n is the unit vector parallel to this one. So you need to compute the vector p minus q and divide it by its own magnitude to find n hat. And in here, dq must be obtained as a lambda. Lambda is the charge density. Q is distributed over 2 pi r, and arc length. And phi is defined in here. So in this manner, we can compute the electric field. Here, even though we, in principle, we can do it by taking the integral. However, every charge is placed in here. The contributions are the same. So this integral will be trivial. And because of the symmetry among this contribution, it is always decomposed into two pieces. That is a parallel to z-axis and that is normal to z-axis. If you do the calculation in opposite position, that force, that electric field is just a mirror image of this. So the normal component, these two components cancel exactly, and only the parallel component along the z-axis survives. Therefore, this integral doesn't have to be carried out. Instead, what we have done is just multiply cosine theta, and cosine theta is not the same. It is not the same as a phi. Instead, it is an angle theta. Okay. That angle theta can be computed using these simple identities. And even though we do not carry out the explicit integral, this cosine theta is replaced with those values. Here, r is the radius and z is the perpendicular distance from this ring to that field point. As a result, we can obtain the electric field at a point that is normal to the circle and passing the symmetry axis. we can see if we substitute z equals 0, it is a 0 because of the symmetry. If z increases to a very large number, then r can be neglected and it becomes something like z over z cubed, and it is proportional to 1 over z squared. Okay. This is a simple application, repeated application of a parallel plate capacitor. If you make use of Gauss law, if there is a charge, surface charge density sigma, then electric field diverges if it is positive with 2 epsilon 0 and sigma over 2 epsilon 0. You can make use of this result by substituting this one in here, 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 and use the superposition principle to add the 3 components, and you will find this answer.